Hello, here we go with N30, 30, continuation of intermolecular forces, or IMFs. This time we're going to go a little bit in depth from our introduction we saw last time. So, first IMF we're going to jump into is hydrogen bonding. Again, understanding that hydrogen bonding requires hydrogen bonded to NO or F. Showing us the hydrogen bond here in the dashed black line. Where's my mouse? There it is. The electropositive hydrogen attracted to a lone pair that is on this nitrogen. No, you can't see the lone pair, but we know that it is there. So again, hydrogen bonding requires hydrogen bonded to N, O, or F, and that electropositive hydrogen attracted to a lone pair on NO or F. This showing between water and ammonia. We're all familiar with DNA, so our hydrogen bonds looking at thymine and adenine. And again, cytosine and guanine showing, again, the hydrogen bonded to a lone pair of electrons on N, O, or F. So, again, we know that the very electronegative atom, N, O, or F, is bonded to a hydrogen. Because it is very electronegative, being up there top right-hand corner of the periodic table, pulls those electrons a lot within that bond, making hydrogen more positive. Because hydrogen has no other electrons, when those electrons are pulled away as part of the bond, the nucleus of that hydrogen becomes de-shielded. It's just a big, strong proton that is very, very positive. Again, it is not a full positive. It is a partial positive, but mainly because the electrons are being pulled away, which results in the exposed proton being a very strong center of positive charge that again can be attracted to a lone pair of electrons of some other molecule. Forms our very, very strong hydrogen bond, because again, all these IMFs we're talking about is an attraction of opposite charge, but again, they are not a full charge like ions, so keep that one in mind. Any questions so far? Okay. Another image kind of showing hydrogen bonding, one space filling model, the other electrostatic potential map. Again, we can kind of see where those positive sides and partial negative sides are, again, forming that attraction. More images to check out, again, looking at water molecules and how they are going to be attracted to one another, as well as some examples of ethanol. Again, the OH in ethanol, the hydroxide group, or hydroxyl, makes a possible hydrogen bond with, again, a lone pair on NO or F. So hydrogen bonds, we know they are very strong intermolecular forces. Of the three, they are the strongest. They are stronger than dipole-dipole or dispersion forces. But please remember that if something has hydrogen bonds as the strongest force of attraction, it still has dipole-dipole and it still has London dispersion. It's just that hydrogen bonding is the strongest. Because it's the strongest, it's going to affect properties. Boiling points, melting points are going to be higher. Stronger bond takes more energy to break the bond. We saw that with delta H back in thermodynamics. But again, even while hydrogen bonds are very, very strong IMFs, they are not nearly as strong as actual covalent bonds. So an actual covalent bond holding hydrogen and oxygen together within water, intramolecular, way stronger than the bond between one water molecule and the other water molecule attracted to it. So, effective hydrogen bonding on boiling point, as we said, it's going to make things a little bit higher. Here's ethanol versus dimethyl ether. Both have identical formulas, identical mass, different structure, has a very large difference in properties, as you can see here, just because of hydrogen bonding versus not having hydrogen bonds. And dimethyl ether just happens to be a polar molecule, or dipole-dipole forces. Any questions on hydrogen bonding? Alrighty then. Next one, dipole-dipole attractions, the one in the middle. We know all polar molecules have a permanent dipole, hence dipole-dipole attractions. Bond polarity and shape are going to play a role. So really got to kind of know your Vesper shape for all of this, not just dipole-dipole. So again, Vesper shapes will come into play, as well as what atoms are used to create polar bonds. So you got to know your electronegativity trend of the periodic table. You have to have a dipole moment. If you do not have a dipole moment within that molecule, you're not going to have dipole-dipole attractions. And then, the always present induced dipole, polar molecules have the ability to induce a dipole in other molecules, because they have a permanent dipole. So it can cause electrons to move around and create a dipole to form that type of attraction needed to form a bond. Again, these are intermolecular forces, not intramolecular forces. The permanent dipole, because of dipole-dipole attractions, adds to the attractive force between molecules. So again, if we're going from London to dipole-dipole to hydrogen bonding, properties are going to be affected. Boiling points, melting points are going to be higher with dipole-dipole attractions relative to non-polar molecules of a similar size or shape, because it is a permanent dipole, whereas we know non-polar molecules experience London dispersion forces, which are temporary dipoles. So permanent versus temporary. Any questions on this one? Alrighty then. So just, again, more pictures to kind of support what's going on. Looking at a polar molecule next to its polar molecule, we can see that there's a positive and negative side. It doesn't change, so it forms that attraction. Looking at a comparison, formaldehyde versus ethane. Yes, they have different formulas, but, almost identical molar mass. But again, ethane is nonpolar. Formaldehyde is polar. So a dipole-dipole attraction versus a London dispersion attraction. We can see here in the chart that melting point, boiling point is going to be much higher comparatively to each other. Again, looking at dipole moments having to affect boiling point, taking these molecules going from propane, which is nonpolar, dimethyl ether is polar, ethylene oxide polar, acetaldehyde polar, acetonitrile polar. They all have very close to each other molar masses, but you can see the boiling point is going up as the polarity is going to increase. More polar, larger dipole moment, stronger attraction. Therefore, boiling points and then melting points also can increase or will increase. Questions on dipole-dipole attractions? Alrighty then. So our last one, London dispersion, named after Fritz London. Again, temporary separation of charge. Excuse me, meaning the electrons are moving around. At any given moment, those electrons are on one side of the molecule or atom, and it creates a temporary dipole. As we said earlier, all nonpolar molecules and noble gases use London dispersion as their strongest IMF of attraction to hold them together, again, in the liquid and solid state. London forces, interestingly enough, increase with the size of the molecule, and an increase in the number of electrons. More electrons you have, larger temporary dipole that can exist. So these fluctuations in electron distribution in atoms and molecules results in a temporary dipole. The fancy buzzword is polarizability. So polar, as in a polar bond, for an example, if the electrons move around, and as we said, any given moment, they are on one side of the molecule, they create a temporary dipole or a temporary polar molecule or atom. Creates a region of excess electron density, greater partial negative charge. Also going to create a region of depleted electron density, which is going to produce your partial positive charge. Again, everything in IMFs, partial negative, partial positive, a quote-unquote full negative, full positive, are ions only. We are not dealing with ions or ionic compounds right now. So these attractive forces of partial negative and partial positive create a temporary dipole, which again are called dispersion forces, also known as London forces. Questions so far? Alrighty then. Continuing along, I've said this multiple times, all molecules and atoms have London dispersion forces. It may not be the strongest force of attraction within the IMF, but everything has London because everything has electrons. Now, the interesting thing is, take any nonpolar molecule or noble gas, at any given moment, its temporary dipole can cause a neighboring molecule or noble gas to also form a temporary dipole. So it induces a dipole in another atom or another molecule, creating the attraction. It goes away, it comes back. It goes away, it comes back, over and over again. That's why they're very weak forces, but they do actually exist. One image, for example, if we're taking a snapshot of things, in frame 1, we can see the electrons are just kind of, one in the center, one on the side. In frame 2, they're on opposite sides. But then at any given moment, we get frame 3, where both electrons are on one side of the atom, creating that higher electron density, partial negative, and the other side, the right-hand side of frame 3, electron depleted area, or partial positive. Now again, electrons are bees around a beehive, so this is just, it happens and then it doesn't. It happens and then it doesn't. But again, if it gets next to another atom in its frame 3 position, it can induce frame 3 in a neighboring atom, partial negative, partial positive. They form an attraction. The atoms stick together. Questions on this? Alrighty then. Another one, again, showing this instantaneous dipole or the induced dipole. The atom on the left-hand side can induce it to the middle one, which can induce it to the one on the right, over and over again until you get a huge sample of these atoms, and you end up getting the liquid state, possibly, because everything's attracted to each other with the partial positive and partial negative, based on temperature and conditions. That's irrelevant at the moment. But again, that's what an induced dipole or instantaneous dipole is kind of referring to. Questions so far? Alrighty then. So the size of the induced dipole, we are still focusing on London forces. So the magnitude of the induced dipole depends on several factors. First one, brought it up earlier, the polarizability of the electrons. How easy or difficult is it to get the electrons or have the electrons just happen to be on one side versus the other? Well, that comes down to the volume of the electron cloud. How big is this electron cloud we are referring to? Now, again, electron cloud, we are meaning within a single element, the noble gases, or it could be the entire electron cloud within a molecule that is nonpolar. Larger the molar mass of your molecule or atom equals more electrons, larger electron cloud, therefore increased polarizability, which then has to lead to stronger attractions. That partial negative and that partial positive are going to be larger. Shape of the molecule is also going to play a role. Look at its Vesper shape for one. Is it one that, like trigonal planar, can lay flat? Is it one that is tetrahedral, that is a tetrahedral? I couldn't think of a better one. I'm sorry about that. But it comes down to how close molecules can get to each other. So if there's more surface-to-surface contact, it's a larger induced dipole, therefore a stronger attraction. So take, for example, as I said, trigonal planar. Trigonal planar molecules could probably stack really well on top of each other and below and next to, whereas a tetrahedral next to another tetrahedral wouldn't be able to get that close to one another. So that kind of idea when it comes to the shape of the molecule leading to the strength of attraction. Questions on this? Alrighty then. So, the effect of molecular size on the size of the dispersion force. Here we're looking at the noble gases. Larger the noble gas, larger the electron cloud, larger the polarizability, larger the attraction. Kind of goes straightforward in that sense. So looking at it, again, molar mass also has to do contributing to this idea. Molar mass is looking at the nucleus, and we're kind of also focusing on the electron cloud, but what comes with larger molar mass has to be more electrons, stronger dispersion force, your boiling point, and your other properties are going to increase. Going back to the shape effect, here we are with pentane versus neopentane, identical molar mass, identical elements within the compound, molecules, but we can see that the shape of N-pentane, they sit very close to each other. It's a larger area of attraction, whereas neopentane doesn't have much area of attraction comparatively. So N-pentane on the left has to have a larger dispersion force, larger induced dipole because of the surface area argument. Continuing along, look how big you are. Go from pentane to hexane all the way up to nonane. Looking at hydrocarbons, boiling point is going to go up with the larger molar mass, more electrons, larger electron cloud, stronger attractions. Boiling point has got to go up. So all these factors we need to take into thought. I can't think of the word right now, I'm sorry. But take into account. There it is, the word account. I figured it out. All these things need to take into account in order to determine what's going to have a higher boiling point. Or if you're asked to rank things, you can't just go based on one singular thing. Graphically, again, looking at attractive forces, we can see straight down the left, water, HF, ammonia, CH4. Again, the top three are hydrogen bonding. The bottom one, methane, is not hydrogen bonding. So we can see a huge jump there. But then going from the blue line, oxygen to sulfur to selenium to tellurium, we see a trend. So they kind of share similar trends as you go down the groups. The black one has to do with the halogens. As it says, group 6, group 7. So you can kind of see a trend forming based on what's involved, size of the electron cloud, more electrons, higher properties, except obviously we see that hydrogen bonding is pretty strong on its own accord. Questions so far? Alrighty then. Alright, the ion dipole attraction. What happens when we do dissolve ionic compounds into water, well, obviously, water molecules will be attracted to a full permanent charged thing, or charged ion. Larger the charge, greater the attraction. Either a larger negative, a larger positive. You can see the orientation of water molecules based on these two different ions and how they change. College Board will sometimes ask you to draw water molecules around ions. You need to be very sure in the orientation in which you draw them. It will make a very big difference. So again, ion dipole attractions form when ionic compounds attracted to polar molecules. So again, salts dissolving in water. Pretty self-explanatory in that sense. Strength of attraction depends many factors, which also affects solubility. Some ionic compounds are more soluble than others. If the ionic compound has a very, very strong bond, high lattice energy, less likely water is going to be able to get in there and separate the ions, whereas compounds with a lower lattice energy, then they can be broken apart and water can separate those ions. Ion dipole would fit above hydrogen bonding in their strength, but below ionic and metallic. So ion dipole is going to be stronger than hydrogen bonding because on one side of it, you have a full charged ion, whereas hydrogen bonding by itself is still partial positive, partial negative. Questions on ion dipole? Alrighty then. So, quick little summary. We know dispersion forces are the weakest of the IMFs. We know dispersion forces are present in all molecules and atoms. The magnitude of the dispersion force increases with molar mass because you get more electrons in a larger cloud, which leads to larger polarizability, which leads to a stronger temporary dipole. Polar molecules also have dipole-dipole attractive forces because you're dealing with a permanent dipole existing due to it being polar. We know hydrogen bonds are the strongest of the IMFs. We know hydrogen bonds are present when a molecule has hydrogen directly bonded to oxygen, nitrogen, or fluorine. And again, realize that the hydrogen is attracted to a lone pair on the other atom. The only example of hydrogen bonding to fluorine is HF. Keep in mind, HF is a weak acid. Acids and bases will come up later. Always got to be aware. Acids do not follow all the rules. So just be aware of that one. Ion dipole attractions are present in mixtures of ionic compounds and polar molecules. They are technically the strongest attraction. Notice up above, it's hydrogen bonds in pure substances. A mixture is not pure because it's two or more things mixed. As I said, ion dipole attractions are the strongest intermolecular attraction that exists. Ion dipole attractions are especially important in aqueous solutions of ionic compounds. So again, dealing with solubility, again, another part we'll get into later this semester. Questions on the summary? All righty then. So lastly is a chart that kind of summarizes everything we've talked about a little bit today. This chart is in your reference section, I believe, for this one. I'll double check on that one. Very important one to probably print out, put in your notes and have, or at least know where you can get it. Questions on this diagram? Alrighty then. Thank you very much. We will see you next time.